Okay, so till now we have looked at the definitions of a differential equation along with the accompanying terms in it. We have looked at how to form or construct a differential equation. We have looked at examples giving us a meaning to the word solution of a differential equation. Next, we will look at how to solve differential equations. Of course, we will be visiting these terms again and again through examples to solidify our understanding of these terms. So let us begin with one of the first and most primitive methods of solving a differential equation, which generally is used when you are at an advanced stage of understanding differentiation. Let's take a look at the first of these visual inspection methods. So this is called the inspection method of solving differential equations. Inspection method. Methods of solving a first order, first degree differential equation. So this method cannot be used for differential equations of order greater than 1, degree greater than 1. That is because when we differentiate a function once, it results into certain simple expressions which we can predict as differential coefficients of x and y. When it is higher order differential equations, then it becomes a little harder to predict just by visual inspection. You have to do certain calculations. So that is why inspection method could be used to solve differential equations. This is not the only way to solve first order, first degree equations, but then could be used as a shortcut method to solve the first order and first degree differential equations. For example, if the given differential equation contains the term x dy minus y dx as a term, then its multiplication by 1 upon x square gives us x dy minus y dx upon x square, which can be simply written as the differential coefficient of y by x. How do we know this? Well, if you are asked to differentiate with respect to x the term y upon x, where x is the independent term and y is the dependent term, by quotient rule you get x dy by dx minus y dx upon dx divided by x square. Removing the dx, we get x dy minus y dx by x square as d of y by x. Here we have removed this dx term from both sides, and so we get x dy minus y dx upon x square as d of y by x. So if we have to solve a certain differential equation containing this term on the right side, that is, we have to integrate an expression like this, then it is equivalent to integrating this expression, which is simply integration of d of y upon x. And since integration is the reverse process of differentiation, the integration of this gives us simply the expression y upon x, which is much easier than having to integrate this particular expression. By the same method, if we have an expression containing x dy minus y dx upon y square, it is equal to minus of d of x upon y. You can again verify this by differentiating with respect to x the expression minus x upon y. You will get x dy minus y dx upon y square. Similarly, if we have expression x dy minus y dx, if it's multiplied by 1 upon xy, you can write it as derivative of d of log of y upon x. Again, differentiating log of y upon x with respect to x, you get x dy minus y dx upon xy upon eliminating dx. Similarly, 1 upon x square y square, x square plus y square, when multiplied by x dy minus y dx, gives us d of tan inverse y upon x. And similarly, x dy minus y dx when multiplied by 1 upon x into root x square minus y square gives us d of sine inverse y upon x. So which term you multiply the numerator with depends upon what you want. Now in all of these, x dy minus y dx is the term that is constant. Depending upon what we multiply it with, we get different terms. In the first term, we got y upon x simply. In the second, we got minus of d of x upon y. In the third, we got d of log of x y upon x. Fourth one, we got d of tan inverse y. Fifth, we got d of sine inverse y upon x.